Imagine this. No stars, no planets, no space, no time. Not empty, not dark, nothing. Then without warning, everything begins. Not with an explosion in space, but with the birth of space itself. Tonight, I want to tell you the story of the universe, how it was born, how it grew up, and how one day it will quietly fade away. People often imagine the beginning of the universe like a firecracker, a loud bang, matter flying outward, an explosion inside space. That picture feels natural, and it's completely wrong, because for an explosion, you need space first, room for things to fly into. But at the beginning of the universe, there was no room, no distance, no direction, no outside. There wasn't even a before. Time itself hadn't started ticking yet. So when we say the Big Bang, we're not talking about a bang at all. We're talking about a moment when space and time came into existence together. That's already strange, so slow down and really feel that. You didn't have empty space waiting around like an empty stage. The stage itself was born everywhere at once. Harry's the part that bends people's minds. The Big Bang did not happen at one point in space. It happened at every point. Every place you look today, your room, the moon, distant galaxies, all of it was once squeezed into an unimaginably hot, dense state, not piled together inside space. Space itself was compressed. A helpful picture is the balloon analogy, but let's do it carefully. Imagine a balloon with dots drawn on its surface. Those dots represent galaxies. Now you blow up the balloon. Each dot moves away from every other dot, and from the point of view of any dot, it looks like everything else is moving away. Which dot is the center? None of them. The center isn't on the surface at all. That surface is the universe. And the expansion isn't galaxies flying through space. It's space itself stretching. So when we say the universe is expanding, we don't mean things are rushing away from a central explosion. We mean the ruler you'd use to measure distance is getting longer. Now let's rewind all of that. Run the cosmic movie backward. Galaxies get closer, space shrinks, temperatures rise. Eventually, atoms can't exist anymore. Then nuclei fall apart. Then even protons and neutrons dissolve into something deeper. We reach a point where everything is so hot and dense that the equations we trust the best ones we've ever built simply stop working. And this is important. Physics doesn't say something magical happened. Physics says, I don't know. That's not a failure, that's honesty. Our theories point back to a boundary wall where space, time, energy, and matter blur together into something we don't yet understand. We call that boundary the Big Bang. But the name can fool you. It wasn't a thing inside the universe. It was the birth of the universe itself. Now here's a subtle but crucial idea. The Big Bang was not the beginning of matter and time. It was the beginning of time itself. Asking what happened before the Big Bang is like asking what's north of the North Pole. The question sounds reasonable, but it assumes something that doesn't exist. Time didn't start running inside a bigger clock. The clock itself turned on. And that should make you uncomfortable, because it means the universe is not just stranger than we imagine. It's stranger than we can imagine. But that discomfort is useful, because every time physics has honestly said, we don't know what's going on here, a deeper understanding eventually followed. Quantum mechanics came from that kind of confusion. Relativity came from that kind of tension. So when the universe tells us at its very beginning, I'm not going to explain myself yet, that's not the end of the story. That's the invitation. And from that strange, silent beginning, everything else follows. Once the universe begins expanding, something very simple and very powerful starts to happen. It cools down. Not because anything is blowing on it, not because heat is escaping into something else, but because expansion itself spreads energy out. Think of a cup of hot coffee on a table. It cools as heat spreads into the room. Now replace the coffee with everything, and replace the room with nothing. There is no outside. Yet the same idea applies. As space stretches, energy thins out. And when energy thins out, temperature drops. That cooling is the reason anything exists at all. At the very beginning, the universe is too hot for structure. Not just uncomfortable hot, not lava hot, not even star hot. So hot that matter can't exist. There are no atoms, no particles. Just raw energy, chaotic, restless, everywhere. But as the universe expands and cools, the first change happens. Energy begins to turn into particles. This is one of the strangest facts in physics. Energy and matter are interchangeable. Cool things down enough and energy condenses into mass. Particles flicker into existence, and just as quickly many annihilate each other. For a while, the universe is a violent foam, particles appearing, colliding, vanishing. But cooling keeps going. And eventually, some particles survive. A little later, still early, but now seconds instead of fractions, protons and neutrons form. For the first time, there are ingredients for atoms, but it's still too hot to assemble them. Imagine trying to build a snowflake inside a furnace. That's what the early universe is like. So the universe waits. It keeps expanding. It keeps cooling. Minutes pass, then years, then hundreds of thousands of years. Finally, the temperature drops enough for electrons to stick to nuclei. And suddenly atoms appear. Hydrogen, helium. The universe becomes transparent for the first time. Light, which was once trapped in the hot fog of plasma, is finally free to travel. That ancient light is still around today. It fills the universe. It's the faint afterglow of creation itself. But even now, the universe is dark. No stars, no galaxies, just enormous clouds of hydrogen and helium drifting through expanding space. Gravity is working, but slowly. Over millions of years, tiny differences grow. Denser regions pull in more matter. Clouds begin to collapse. And then, after hundreds of millions of years, the first stars ignite. This is a turning point, because stars don't just shine. They manufacture complexity. Inside a star, gravity crushes atoms together with tremendous force. Hydrogen fuses into helium, helium into heavier elements, carbon, oxygen, neon, silicon. And in the most massive star siren, these elements are not leftovers from the Big Bang. They are forged, built under pressure, paid for with energy. And when massive stars die off and violently, they scatter these elements into space, seeding future stars, future planets, future chemistry. This means something extraordinary. The early universe gives us simplicity, hydrogen, helium, light. But stars give us possibility, rocks, oceans, atmospheres, cells. Every atom in your body except hydrogen was created inside a star that lived and died billions of years ago. So when people say, you are made of stardust, that's not a metaphor, it's a historical record. Your atoms have a past. They remember a time before Earth, before the sun, before there was anyone to ask these questions. And the cooling universe made all of it possible, because without cooling, there is no structure. Without structure, there are no stars. And without stars, there is no story to tell. For most of the 20th century, cosmologists thought they understood the universe's future. The universe began expanding fine, gravity would slow it down, of course, matter pulls matter together. That idea felt almost obvious. Throw a ball into the air and it comes back down. Gravity always wins. So the great cosmic question wasn't if the expansion would slow, but how it would end. Would the universe eventually stop expanding and collapse back on itself? Or would it coast forever, slowing more and more as time passed? Either way, gravity was in charge. Or so everyone thought. Then, in the late 1990s, astronomers decided to do something clever. They looked at very distant exploding star supernovae, because these explosions shine with a known brightness. If you know how bright something really is, and how bright it appears, you can tell how far away it is. These stars were meant to be cosmic measuring sticks. The astronomers expected one simple result. Distant galaxies should be slowing down. But when they checked the data, the universe gave a completely different answer. The galaxies weren't slowing. They were speeding up. This wasn't a small correction. It wasn't a rounding error. It was the kind of result that makes scientists assume something is wrong with the equipment. So they checked again. And again. Different teams, different telescopes, Same conclusion. The expansion of the universe is accelerating. Something is not just letting galaxies drift apart. Something is pushing them apart. Now pause for a moment and feel how strange that is. Every force you've ever experienced pulls things together or resists motion. You push a box, it resists. You drop an object, it falls. You stretch a spring, it pulls back. But here is something different. A force built into space itself. A pressure that doesn't clump matter. It separates it. We call this mystery dark energy. Not because it's spooky, not because it's evil, but because we cannot see it, touch it, or describe it properly. The name is a label for ignorance. Here is what we do know. Dark energy doesn't behave like matter. It doesn't thin out as space expands. As the universe gets bigger, dark energy keeps doing its job, pushing space to expand even faster, which means the emptier the universe becomes, the stronger this effect appears. That's deeply counterintuitive. You'd expect emptiness to mean nothing happens. But in our universe, emptiness is active. Space itself has energy, and that energy has consequences. This discovery quietly rewrote the future of the universe. No dramatic announcement, no alarm bells, just a realization. Gravity is no longer in full control. Galaxies that are already far away will never come back. Eventually they'll move away faster than light can cross the gap, not because they're breaking the speed limit, but because space between us keeps stretching. Over time, the night sky grows emptier. Distant galaxies fade, then vanish. Civilizations, billions of years from now, may look out into the universe and see only their own galaxy with no evidence the rest ever existed. Not because the universe ended, but because it expanded too much to observe. And here's the most honest part of the story. We don't know what dark energy is. We don't know why it exists. We don't even know if it will remain constant forever. But its discovery reminds us of something essential about science. The universe is under no obligation to match our expectations. Just when we think we understand the ending, the story changes, and that change determines everything that comes next. Because the fate of the universe is no longer just about gravity pulling inward. It's about something unseen, woven into space itself, quietly deciding how the cosmos grows old. Now let's talk about the end. Not the kind of ending we're used to. No fireball, no cosmic collapse, no final explosion that wipes the slate clean, just fading slowly, relentlessly. As the universe keeps expanding, something subtle but unavoidable happens. Everything spreads out. Stars burn fuel. Fuel runs out. Stars dim. The bright, busy universe we know today is living off stored energy-concentrated pockets of order, fighting a general trend toward disorder. And that trend always wins. This isn't pessimism. It's thermodynamics. Think about a hot cup of tea left on a table. At first there's a difference. Hot tea, cooler room, heat flows. The difference shrinks. Eventually, the tea and the room reach the same temperature. At that point, nothing interesting happens anymore. No heat flows, no work can be done. The universe is doing the same thing, just on the largest scale imaginable. As trillions of years pass, stars exhaust their nuclear fuel. Some collapse into white dwarfs, others into neutron stars, some into black holes. Galaxies stop forming new stars. The sky grows darker, not suddenly, so slowly that no single moment feels dramatic. But direction matters. Eventually, even stellar remnants cool. White dwarfs fade to black. Neutron stars decay. Black holes since thought eternal vary, slowly evaporate. And what's left? Particles drifting farther apart than any force can meaningfully pull them together. Energy is still there, but it's evenly spread, too evenly spread. This is the key idea. The universe doesn't run out of energy. It runs out of useful energy. Energy differences are what make things happen. Hot to cold, dense to empty, high to low. When those differences disappear, the universe hasn't died violently. It has gone quiet. Physicists call this state heat death. A universe with energy everywhere and nowhere to use it. No light, not because photons vanish, but because nothing emits them anymore. No heat not because energy is gone, but because there's no colder place for it to flow. No motion with purpose. No chemistry. No complexity. Just an endless, thin, uniform bath of particles and radiation. Time still exists. But nothing meaningful changes. And this is the strange part. Heat death is not a catastrophe. It's the most natural ending imaginable. If the universe keeps expanding, if entropy keeps increasing, this outcome isn't dramatic, it's inevitable. The universe doesn't fail. It completes the rules it started with. That quiet ending can feel unsettling, but it also tells us something profound. Everything interesting, stars, planets, life, thought, exists because the universe is not yet finished. We live in the brief era where differences still exist, where energy still flows, where complexity is possible. The universe is not rushing toward an ending. It is relaxing, stretching out, letting go of tension, difference, and structure. And one day so far in the future that numbers almost lose meaning, it will reach perfect calm, no drama, no audience, just silence. And that silence, strangely enough, is written into the very laws that made everything possible in the first place.